Good morning, everybody. My name is Matthias Bolton, and it's a pleasure for me to announce early career prize lecture this morning. And you will have seen that this year's prize goes to Edgar Solomonik. He is an assistant professor at the University of Urbana-Champaign at the moment, at the University of Illinois in Urbana-Champaign at the moment. He did receive his PhD from the University of California in Berkeley in 2014. Afterwards, he was a postdoctoral researcher at ETH Zurich. He did receive numerous prizes, the Alston Household Award, the David Zackerson Memorial Prize, and the IEEE TC-HPC Award for Early Career Researchers in High Performance Computing. And before he's going to provide his prize lecture that is titled Scalable Algorithms for Tensor Computations, I'll like to hand this plaque to him that is awarded together with the prize. Edgar. And now we are looking forward to his talk. And I wish you a lot of fun listening to it.
Thanks, Matthias, for the very generous introduction, and it's a great honor to receive this prize. So today I'll talk about matrix factorizations and tensor computations. Much of the work I'll talk about will have been done by my group at Illinois, which now includes 6 PhD students, and we work on a variety of topics, which range from parallel matrix factorization algorithms, so for example, QR and eigenvalue problems, to tensor computations. And today I'll talk a bit about tensor decomposition in particular, as well as sparse tensor kernels. One of the main application areas that we work with is the simulation of quantum systems, and I'll talk a little bit about how our tensor methods can be applied to those domains. We also look at fast bilinear algorithms that try to exploit tensor symmetry and to try to derive new fast algorithms for convolution and fast matrix multiplication using tensor decomposition. Okay, so I'll start by talking a little bit about our results in communication avoiding algorithms for matrix computations. And those will include the result that I was kind of nominated for this award, which was a paper on communication avoiding eigenvalue algorithms for the symmetric eigenvalue problem. Then I'll talk quite a bit about tensor computations, and there I'll go a little bit faster, summarizing a variety of results, mostly done recently within my group. One of the major lines of work during my PhD, and a line of work that we're still continuing, but one that also goes back to actually the 1980s by works by Mark Snur, among others, is to try to find algorithms that are three-dimensional for matrix factorizations of various sorts, which is relatively easy to do for matrix multiplication and reduces both communication and synchronization cost, but it's quite a bit more challenging when it comes to other problems such as triangular solve, LU factorization, or the symmetric eigenvalue problem. And in general, the goal here is to use some number of copies, for example, C, of the matrix, in addition to the first copy, to reduce communication by a factor of square root C. So there's a trade-off here between memory footprint and communication, and in fact, there's a trade-off between also communication and synchronization. The product of the two has to equal n squared, which is something that we have proved in terms of lower bound analysis. And this holds for a variety of matrix factorization algorithms. We've looked at trying to derive 3D algorithms for triangular solves, LU with pivoting as well as without pivoting, QR factorization, and the symmetric eigensolve. For some of these problems, like LU and QR, a previous theoretical work has been done by Alexander Ratiskin that achieves the desired 3D costs in the BSP model. One of the things we've done for those problems is to make things a little bit more practical and show that speedups can be achieved on actual architectures today. But for the symmetric eigenvalue problem, we actually had to do quite a bit of transformations to how it's usually computed in order to be able to achieve the desired 3D costs. Although we can only currently compute eigenvalues, for eigenvectors we require a bit more computation than asymptotically desired. There's a log factor there. Let me first mention actually a little bit of work that's been done in my group more recently by Tobias Wicki, who designed an algorithm for a triangular solve that is based on inverting diagonal blocks in order to reduce both the depth of the algorithm as well as the communication costs, both in terms of latency and bandwidth within the TRSM problem, no matter the number of right-hand sides that we're trying to solve for. And the key insight here is that the inversion of a triangular matrix can be done with logarithmic depth in terms of parallelism, as opposed to linear depth in the usual triangular solve technique. So the result is that we can decrease the synchronization costs, so the number of times processors have to talk to each other, by a factor of p to the 2/3 on p processors, and we obtain an optimal communication no matter the number of right-hand sides. Another recent piece of work that shows the practicality of some of these approaches is done by Ed Hutter, who actually presented this just yesterday, showing that the Cholesky QR2 algorithm, which does what we were always told not to do, Cholesky QR for QR factorization, which is not stable, but if you iterate it one more time, you're generally achieve good stability, and if you iterate it 3 times, then you are guaranteed to achieve perfect stability. What we've shown is that with 2 iterations on a large number of nodes, this can outperform scale-it-back by a fairly large margin due to both less communication asymptotically, as well as better efficiency by leveraging large matrix multiplication kernels locally. But now let me talk a little bit about the symmetric eigenvalue problem algorithm that we came up with. So the major bottleneck in kind of the state-of-the-art algorithms for the dense symmetric eigenvalue problem are based on doing orthogonal similarity transformations that reduce the matrix to a tridiagonal matrix with the same eigenvalues. This is typically done by successive QR factorizations and with a Q factor applied from the left and the right-hand side. The fact that these updates are 2-sided as opposed to 1-sided in QR factorization makes this quite a bit harder to actually manage, and I'll show one example of the bottlenecks and challenges that this poses. To actually be efficient, what's often done is QR factorizations on B columns at a time that reduce the matrix to a banded matrix first, as opposed to a tridiagonal matrix, and we'll see why this is good shortly. The traditional algorithm that's been implemented in lateback and scale-it-back typically goes directly to tridiagonal, but that's been shown to be suboptimal in modern architectures. The reason for that we can find by looking at the householder form of the Q orthogonal matrix applied to A. So this would be one transformation done in this 2-sided reduction process. And a bottleneck there is the fact that we need to multiply A by one of these U matrices. In the case of going directly to tridiagonal, this would be a matrix vector product, which has an arithmetic intensity of O of 1. So that here there would actually be a memory bandwidth bottleneck associated with moving A from memory to cache and back. And this can be observed to slow down both scale-it-back and lateback quite a bit for the step of problem. So the idea, which goes back quite a bit to work by Lang as well as others, is to first reduce to a banded matrix. And while doing that, in a sense, moving A fewer times between memory and cache. So this improves the vertical communication cost, which we sometimes call the amount of data moved in the cache hierarchy. After that transformation, we have to go from a banded matrix to tridiagonal. And the reason that this is easier is not only the fact that the computational cost is lesser, but also that the memory bandwidth cost is less. Now moving A between memory and cache is easier because A has fewer entries. However, there are some major challenges. These transformations on the banded matrix will introduce fill. So we actually have to chase bulges down the band and typically leverage some kind of pipeline parallelism in the process in order to be efficient. So whenever we apply such a single QR factorization in a 2-sided way, there is fill introduced here. However, we know how to do that efficiently, and that's due to work by Gray and Nick Knight with Jim. And so the state of the art for this type of problem has been actually shown to be quite a bit more efficient. So to do this 2-stage reduction versus the 1-stage reduction in the ELPA library. And if we try to analyze theoretically what happens, we see that the amount of communication is like n squared divided by square root p, which is typical of 2D algorithms for matrix factorizations on a 2D grid. And the synchronization cost is square root p log p squared. Our approach takes this route somewhat further. We actually don't just do a single reduction to band, but we reduce between many different bandwidths one-to-one. And what we find is actually in the limit of trying to do a 3D algorithm, one has to reduce the bandwidth by a factor of 2 at every step. And then in the end, you end up with log p stages of band reduction. And theoretically, this can be shown to reduce the communication cost by p to the 1/6 if everything in the process is parallelized correctly. This is for the forward transformation stage of actually computing the eigenvalues. There are further challenges in actually making this possible. One is to be able to do QR factorization communication optimally using a 3D strategy. And the major insight of why one would want to reduce to a thicker bandwidth first is that larger QR factorizations can be done, which we know how to do efficiently, for example, via algorithms like Cholesky QR2. A further challenge is then how to do successive band reduction once we have a thicker band. And to achieve the right cost, one actually needs to do 3D QR factorizations for each one of the QRs that's happening concurrently, and also pipeline across process groups. And if you do all that, we get the desired communication costs. So we can show that the communication is less by p to the 1/6. So this is the amount of data moved by any process to any other process along the critical path. And also the memory bandwidth cost is reduced modulo log factor. And however, the latency goes up a little bit, but we expect that due to lower bound analysis that applies even to simple factorizations like Cholesky. The major problem that's left there is that we don't have a work-efficient way of actually applying the back transformations in order to construct the eigenvectors, since those cost n cubed for each stage of band reduction. So there's more work to do to figure out how to make that possible, or whether it's not possible. Okay, so that's a bit about the work we've done on matrix factorizations. Now I want to talk about another line of work we have on tensor decompositions. So I will use the terminology that a tensor has order n instead of dimension n, which means that it has n modes or indices, and I will say that the dimensions are s by s by s by s. So if you see an s, it denotes kind of what would be a typical matrix dimension, for example. The main decomposition I will focus on in this talk will be the canonical polyadic or Candy-Comp-Parafac tensor decomposition, which expresses a tensor or approximates a tensor by a sum of tensor products of vectors. The most widely used method for this problem is alternating least squares, which forms a quadratic optimization problem for each one of the factor matrices, which consists of the assembly of these vectors into one matrix as well as all of those vectors. The major advantage is that this method always decreases the residual of the decomposition, so one can use this reliably and achieve convergence, but the convergence may be quite slow. In general, it can be shown to be at best linear, and there is experimental observations of ALS being stuck in what are called swamps, where it makes kind of very tiny incremental progress and doesn't really converge. An emerging alternative that I will talk about a bit is the Gauss-Newton method, which comes from nonlinear least squares problems. And the major advantage is that this can achieve potentially a quadratic convergence rate when near the minima. However, a major disadvantage is that the convergence is non-monotonic, so the residual can all of a sudden spike up. One of the results we've achieved for alternating least squares is to try to perform each ALS sweep, so a single sweep updates all of the factor matrices in the decomposition in an approximate way. To do that, we leverage a technique we call pairwise perturbation, which is good when the factor matrices are changing little. And that's exactly when ALS is bad. What happens is that if there is a small change to a factor matrix, the other optimization problems change only slightly, and the first order correction can be made in asymptotically less cost. So for a rank R CP decomposition of an s to the n size tensor, an ALS sweep will cost s to the n times r, so the size of the tensor times the rank. And with this approximate scheme, we can reduce that cost to s squared r, so something that's actually independent of the order of the tensor. And once we actually do this approximately, we can achieve extremely large speedups in different scenarios, for example, 600x. However, of course, life is not perfect. We do need to set up the pairwise perturbation operators to actually start doing approximate steps. So only when we are actually in that regime do we get the benefit. The setup itself costs here as PP initialization, a little bit more than an ALS sweep, while the subsequent approximate steps are very cheap. Typically, one might be able to take 5 to 10, perhaps, approximate steps before one needs to reinitialize due to the fact that things have changed too much. But if we apply this in practice, we generally see speedups of 2 to 3x for a variety of problems. One example is what I believe is here a quantum chemistry tensor example problem where PP converges kind of twice as fast as ALS. And we see that across a range of problems, both in sequential and parallel execution. The same technique actually also applies to the Tucker decomposition, which I won't talk about in detail, but is somewhat different. And there we reduce the cost by something that depends on the ratio of the tensor dimension to the rank. In terms, what we've done for Gauss-Newton looks a bit different. Here we realized when we started to look at the Gauss-Newton method that it's actually quite a bit better at finding minima than ALS. So for example, for the decomposition of a 4x4x4 tensor, which seems very simple, right? We should be able to do that without a problem. And this is in fact a tensor that we construct to have an exact CP decomposition, and then we try to find it. It turns out that ALS can essentially never find the decomposition when the rank is like 6 or 7, it struggles to find it when the rank is somewhere in the middle there. While if the rank is low or high, it's relatively easy for ALS. Well, Gauss-Newton actually converges with much higher likelihood, even if we just use it naively. But the major insight that Navjot came up with is that if we actually use a new regularization strategy, which takes the regularization parameter and oscillates it between 2 thresholds, this convergence probability is yet higher, and we generally find the solution faster. So another example in the quantum chemistry tensor is shown here, where we converge to a much higher fitness score, much faster than ALS or Gauss-Newton with a fixed regularization parameter. And we've done experiments to show that for a variety of regularization schemes, so here's a couple of examples, the varying regularization method is much more robust. We also get better accuracy in terms of approximation, so this is one example, and we especially do better when there's an underlying exact CP decomposition, which is an important problem because that's what we're looking for to discover fast matrix multiplication algorithms such as Strassen. And we've shown that Gauss-Newton is also better in those scenarios in general. We also have observed that this Gauss-Newton method is generally faster than the alternate least squares method, both in sequential execution as well as in parallel execution. And the latter is somewhat surprising, and in fact, we believe this is the first parallel implementation of a Gauss-Newton method, because there's quite a bit of finesse that's needed to actually make Gauss-Newton work. You can't just construct a linear system and solve it as you would for regular optimization problems, but you have to use an implicit conjugate gradient method, which requires many iterations and is in a sense not very parallel. But it is work efficient and can still be parallelized because it consists of tensor contractions that are parallelizable. A different line of work that we've pursued actually partially many years ago and partially very recently is to try to exploit symmetry in tensors. There's a couple of different types of symmetry that arise in tensors, and they're quite prevalent in essentially any quantum chemistry or quantum physics method that uses tensor contractions. One is permutational symmetry. So this is the same type of symmetry we typically see in matrices. And an example in matrices might be to compute a contraction AB plus BA, so a matrix multiply of 2 symmetric matrices plus the transpose, which yields a symmetric output. And our idea was to find a reorganization of this computation that exploits more symmetry in order to reduce the number of multiplications necessary, which is also the bilinear rank of this problem if we consider the bilinear algorithms formulation. And this is very important if each multiplication is more costly than an addition. An example of such a case might be when each entry is itself a matrix, in which case this actually corresponds to a tensor contraction of order 4 tensors. That's exactly what we analyze in this plot, and we observe that this new method can achieve speedups of something like 4.5x, which is close to the 6x reduction that we achieve by the reorganization due to the 3-mode permutational symmetry. While this result is nice and also extends to arbitrary symmetric and anti-symmetric tensor contractions, it's quite challenging to implement because the result doesn't really look like a standard matrix multiplication anymore. A very new result that we're still actually kind of in the process of writing up is to try to do an algebraic reorganization that is effective when the tensors have group symmetry. One example of a group symmetry is a point group symmetry in molecules, which means that each rotation, the system is invariant to rotations. Another example is k-point symmetry, which means that in the reciprocal space, there is some kind of conservation laws we can exploit that follow group properties. And yet another example is quantum number symmetry, which arises in quantum computing computations with tensor networks. For all of those problems and any tensor contractions, we found a method to leverage directly the irreducible representation of the tensors, which is a dense tensor object, to minimize the cost, which is actually asymptotically lower relative to the size of the group. This is actually kind of a radical approach to this problem, which is usually tackled by block sparsity. So instead of using a block sparse tensor, we're able actually to work with everything with dense tensors. And these fancy looking diagrams kind of describe the transformations that are necessary to go from a contraction that has a certain implicit form to a form that we can actually contract efficiently. And this requires a few tricks that are quite non-trivial. And the result is that we get big dense tensor contractions that we can parallelize very effectively and very easily. So this allows us to do quantum chemistry and quantum physics methods using simply dense tensor contractions as opposed to sparse. We've also done quite a bit of work on the practical side of tensor computations. The Cyclops library is something I have been developing now for 9 years, and many other people have contributed. It aims to take what originally were dense tensors, now is dense or sparse, and parallelize them over MPI, so over distributed systems. And do so efficiently. Originally, we worked with C++. Now we also have a Python interface, and we also support generalized operations. So, for example, using semirings for each tensor contraction, or using mixed precision, which can also work in this context nicely. This library has been adapted in quantum chemistry methods, where it allows these large sequences of tensor contractions to be implemented with one line of code each that looks just like the algebra. It's also been used for quantum circuit simulation more recently with really minimal involvement from me. And it's been used, for example, for graph problems such as between centrality. And more recently, actually, we've applied this to Jacquard similarity for bioinformatics applications for genomic similarity. An example of what a contraction might look like in this library is this computation, which computes a residual for a CP tensor decomposition of a certain order 6 tensor, where 2 indices show up in each factor matrix. The core idea internally is that we selected the best distributed contraction algorithm at runtime via performance models that predict the cost of each kernel in terms of communication and work. Our support for Python enables us to be almost a seamless backend to NumPy ND array, which gives you not only distributed memory execution, but also sparsity, without the work of having to work with a CSR representation via SciPy or something similar. And we have GPU support, although it's not completely done for sparsity, but it does work for density, and OpenMP for threading in addition to MPI. We also provide a simple interface to scale back matrix factorization routines, which you can now call via this library from the Python interface in a much simpler interface than the standard scale back one. So within this library, we also support sparsity, as I mentioned. And to do so, we leverage a particular matrix format for each sparse tensor contraction. We support both sparse times sparse, sparse times dense variants. So in fact, any sparse or dense times any sparse or dense into a sparse or dense tensor, everything works. And that can also work for generalized data types. And we see a benefit from sparsity that actually grows as we weak scale, so as we increase both the problem size and the number of processors together. And we also see that within a quantum chemistry method, if we exploit sparsity in different quantities, such as the 2-electron integrals or the amplitudes, we get much better weak scaling. So while at first sparsity has rather little benefit, as we go to larger and larger problems and also more nodes, we get more and more benefit. Although this is kind of somewhat artificial because we're enforcing that the integrals and amplitudes have a certain sparsity. We're not yet at the point where we can take a quantum chemistry code and actually compute the same solution leveraging sparsity, but we're working toward that. We've also realized, however, that it doesn't suffice to do sparse tensor contractions between two tensors at a time. There are operations for which all-at-once contraction between more than two tensors is much more efficient than performing pairwise contraction. One example is the MTT-KRP, matricized tensor times Cauchy-Rao product, which is the bottleneck for CP decomposition of sparse tensors, where we contract a sparse tensor with two dense matrices. And in this case, doing it all at once enables kind of a smaller output, which reduces the communication cost. And we see that there's a huge benefit of doing this. So that's the blue line here is the all at once with CTF versus the red line, which leverages sparse representation until the tensor is so sparse that you need to use a hypersparse representation for matrices, which means that we don't actually store anything if a row is 0. So that's memory efficient, but it is not work efficient. We're not quite as fast as the state of the art, which is splat. So Shaden has done a fantastic job of optimizing that, and we're still 2 to 4x off because we need to, for example, redistribute the factor matrices prior to contraction. Another operation we've identified that's quite important, where all-at-once contraction is yet more critical, is what we call TTTP, tensor times tensor product, which arises in CP tensor completion and also provides a way to compute the residual over sparse tensor CP decomposition in a work-efficient manner. Here, again, all-at-once contraction is critical and allows us to scale to massively sparse tensors where less than 1 in a billion in a million of entries is non-zero. Okay. So to kind of summarize some of the work that I've just described, we have spent quite a bit of effort trying to make more matrix factorization algorithms 3D in order to reduce the communication cost by a fairly small but an asymptotic factor. And we've also shown that these algorithms are often faster in practice. We've developed a few different methods for optimization of tensor decompositions that are more robust and faster. And we've also introduced a library where all of these methods have been implemented. And generally, we can support arbitrary dense and sparse tensor algebra. And finally, I'd like to thank all the members of my group at the Laboratory of Parallel Numerical Algorithms at U of I. As well as some collaborators, including my PhD advisor, Jim Demmel, my postdoc advisor, Torsten Hoffler, and Garnet Chan, with whom we've been collaborating in quantum chemistry methods over the past couple of years. And I'd also like to thank the NSF, the DOE, and TAC for providing us access to computational resources. And finally, I would like to thank SIAM for this award, which is quite an honor. Thank you.